Welcome back, physics fans. Here we are. We're going to do another question here. On the top of a 20-meter high building, a physics student builds a catapult. She fires a 3-kilogram watermelon at a speed of 33 meters per second at an unknown angle. The watermelon reaches a top height of 45 meters, clearing the next building. And at the top height, it's traveling at a speed of 6 meters per second. How much energy was lost to air friction during this part of the projectile shot, the beginning part here? So there's a way that we're going to look at it, and we cannot look at it with kinematics. Reason is because we don't have any formulas for friction. The friction ones are a force, it's not a kinematics one. And we don't even have the launch angle. So we're really hooped here for kinematics. But for dynamics, work, power, energy, we can start with the conservation of energy. So the energy before equals the energy after. So the kinetic energy plus the potential energy plus the spring energy plus how much energy you add in will have to equal the kinetic energy at the end, potential energy at the end, plus the spring energy at the end, plus the heat energy at the end. And I feel very comfortable doing this way, and it's no problem. Just a little bit extra, but you go 1/2 mv squared and mgh, and the m is 3, and the g here is 9.8, and the h is 20, and the initial speed is 33, so it'd be 33 squared. You could just do this. There's no spring energy in either case. That's fine. I'm going to just rearrange this and just put all these initials over to the other side and make them change in energies. And then there's this way of looking at it. That the work is the change in energy. So the work done is how much energy is changed in the kinetic energy plus the potential energy plus the spring energy plus how much is added to the heat. So we're going to look at it this one. So we have the change in kinetic energy, which is kinetic energy final minus kinetic energy initial. Now please don't reduce this down to 1/2 m and then in brackets Vf minus Vi all squared. It isn't. This is going to be a difference of squares. And I'll come back to that. This is mghf minus mghi, and that can be just mg times hf minus hi, plus the heat energy. So we have 0 joules as it's going up in a projectile, and there's no rocket pushing it up, there's no added energy, there's no explosion during it to give it more energy. 1/2 m, 1/2 times 3, and then it's Vf squared minus Vi squared. So it's the Vf squared and then the Vi squared. 12 and 33, 12. And then the mgh is 3 times 9.8. And then the subtraction, the 45 meters is the final height in 20. There's our change in kinetic energy and our change in potential energy. So that it reduces kinetic energy by 1,417. It reduces potential energy by 735. No, it increases potential energy by 735. So the heat must be what's left over because this is lost that much. If there was no air friction, then this would have gained that much. It would have been that much of a height difference. And that's just going to be 682.5 joules. There we go. Good question. Conservation of energy.